introduction. So, hello everybody. I hope you're doing fine. So this talk is about experimental evaluation. I may have prepared too many things, so maybe we won't have time to have a look at everything, but you will have the slides to have a look into details. And also don't hesitate to ask questions. We have a question and answer facility, so please ask all your questions. You can also, of course, take the speak to ask questions. So a very quick introduction to say that, of course, theory is very important, and a lot of properties can be proven by a theoretical analysis. In particular, we can study the complexity of the problem, and we can also study properties of algorithms. But theory has some limits. And when we solve NP-hard problems, a major limit is that all exact algorithms have exponential time complexities. But in practice, we know that some algorithms are very efficient, or at least much more efficient than other algorithms. So the only way to see which one is the best is to perform experimentations. So experimentation is really complementary to theoretical analysis. A few quotations, a few quotes. The first one is funny, but not that important. The last two really say that experience is very complementary to theory. And we have to combine both. And I like the one from Knut, who says that by alternating between theory and experiment, you improve both parts. Okay, so now it's time to deep in the subject. So first, I will have an overview of the experimental process with a focus on reproducibility, how to choose the benchmark instances, and how to measure performance. And then we'll have a study of how to analyze the results with 3 use cases, 3 real experiments, which we are going to compare. And finally, we will have a look into automatic algorithm configuration and selection. So the experimental process is done in 3 steps. The first step is to prepare the experiment. So first you have to identify a question. If you don't have any question, just don't do any experiment. And the kind of question you can have is, for example, what is the influence of a given parameter on the solving process? Or another question, which is quite classical in our domain of research, is my new solver competitive with state-of-the-art solvers? Then you have to design the experiment. You have to identify what you are going to measure and on which benchmark you are going to measure this. And then you have to prepare the test environment. You have to prepare the scripts that will be used to launch the test, and you have also to prepare the infrastructure for computing. Then the second step, which is usually very long, but you don't have to do a lot of things on this step, is to perform the experiment. So it is completely automated, and you simply run scripts and collect the results. Finally, the last step is to analyze the results and to see if you can answer your question. If you cannot answer the question, then you have to go back to the first step and maybe change the question or change something in your experiment. Otherwise, if you have answered the question and if the answer is interesting, then you can publish. So usually we distinguish 2 kinds of experiments. First, we do very short experiments that are used to identify what you should intensively experiment. So what are the relevant questions? What are the parameters that we should study? What are the relevant instances, etc. And then once you have identified all the important things for your experiment, you can prepare an intensive experiment. And in this case, it may have a quite long duration. In some cases, it is up to several months. So a few words about reproducibility. Why do we want to reproduce an experiment? Maybe this is simply to check some published results, but usually it is because we want to compare a new algorithm with an algorithm which has already been published. And usually if you don't compare yourself with state-of-the-art approaches, you will have reviewer will ask you to compare yourself with published results. So it is very important to be able to reproduce an experiment, but it is usually quite difficult. It is difficult because we need to have all information and all tools. And this is not only the source code or the executable code. You also need to have all data, in particular benchmark instances. You need to know all parameter values. You need to have all details on the environment, the processor, the operating system, the compiler. And finally, and maybe this is the more difficult, you need to be able to access to exactly the same machines, the same computers that were used for your experiment, and also all libraries. And sometimes the libraries can no longer be compiled on the computers you have. So this is very difficult to reproduce an experiment, especially if it has been done in 20 or 30 years ago. So a solution which is proposed by Jan Gent is to provide virtual machines. In this case, you can always reproduce an experiment. So this is a really good practice to do. The American Computing Machinery Association distinguished 3 levels of reproducibility. So we simply speak of repeatability if we just yourself, you want to reproduce your experiment with the same benchmark instances and the same environment. The second level is replicability. In this case, this is another team who wants to perform exactly the same experiment. And finally, the third level is reproducibility. And in this case, this is a different team which must be able to reproduce an experiment, but with a different experimental conditions. So yes, Docker is a nice way to make experiments reproducible. Thanks for quoting it. So you can have more details on these 3 levels on this website. Here is a checklist which has been provided for machine learning conference, but I think it is a very nice checklist, and we can use it also for constraint programming and combinatorial optimization conferences. So the first thing to check is that you have a clear description of your algorithm and your mathematical setting, an analysis of the complexity, and of course a link to everything needed to reproduce the experiment. Also, of course, you have to check that you include a statement of your theoretical claims and proof of these claims. And finally here you have a long list of things to check. And actually, if you want to use it for constraint programming or combinatorial optimization, you simply have to replace data with benchmark and everything can apply in our field of research too. So of course you must completely describe the benchmark you have considered, and how do you have collected this benchmark. And we must be able to download this benchmark and also the environment used to generate the benchmark. You must explain why you have excluded some instances. And well, this point is very specific to machine learning. So we usually don't have training and validation and testing samples. Now, the next point is very important. You must explain how you have tuned your parameters, and what parameters or hyperparameters, and what method you have used to select the best parameter configuration. You must precise the number of runs and how experiments have been run, and what are the statistics you've used, and of course error bars or box plots and things like that. Okay, now a point on how to choose benchmark instances. The benchmark you use clearly depends on the question addressed by the experiment, and that's why it is very important to first identify the question you want to address in the experiment. So for example, if your question is my program correct? Then you consider stress test instances. If you're interested in worst case performance analysis, then you identify the worst case instances. If you want to study scale-up properties with respect to instance parameters, which is usually the case in our field of research, then you usually use randomly generated instances, because it allows you to control parameters. If you want to check if your solver scale well for a given application, then you will consider real-world instances. And finally, if you want to compare yourself with state-of-the-art approaches, you have to use public benchmark instances. An important question is whether to use benchmark with very similar instances. We say that it is homogeneous if all instances are very similar. And in this case, it simplifies the analysis of the results. But of course, the results are not very general, because they only apply on a very specific class of instances. So usually we prefer to experiment on heterogeneous benchmark to obtain more general results. But in this case, the analysis of results is more difficult. So we will see that we have to decompose the benchmark into homogeneous classes when analyzing the results. Now, an important point is to choose the hardness of the instances. If we have only extreme instances, that is very easy on instances or very hard instances, in this case, we won't have very interesting results, because the very easy instances are very quickly solved by all algorithms. And very hard instances, well, usually nobody is able to solve them. So it's not interesting to have very easy, to have a lot of course, it's interesting to have a few very easy instances and a few very hard instances, but not only very easy or very hard instances. And it is important to gradually increase the hardness of instances in order to study scalar properties. So it is necessary to have an idea of how hard are the instances. So we have to study the factors that have an influence on hardness. In particular, the size of the input can have an impact on the hardness, but on NP-hard problems, this is not the main factor, and we will have a focus on this in the next slides. For example, we know that the structure of input data has influence on the hardness. If I take example of constraint satisfaction problems, the tree widths of the constraint graph has an influence on hardness, and in particular, if the constraint graph is a tree, then we can solve the instance in polynomial time. Another factor which influences hardness is constraintness, and we are going to have a focus on this in the next slides. So this corresponds to the phase transition phenomena for decision problems. And then we will have a quick look at search landscape, which is used to predict hardness for optimization problems. So phase transition, let us illustrate this on the problem SAT, which involves deciding whether a Boolean formula with n variables and p clauses is satisfiable or not. So this is a decision problem. And we all know that the hardness of these problems depends on the number of variables, but also on the ratio between the number of clauses and the number of variables. If this ratio is very small, it means that we have very few constraints. And in this case, we have an under-constrained instance. And for this instance, it's very easy to find a solution, exceptionally, except for very rare cases for which it will be exceptionally hard. On the other hand, if this ratio is large, it means that we have a lot of constraints compared to the number of variables. And in this case, we have an over-constrained instance, which has no solution. And it is usually very easy to demonstrate that this instance has no solution. And the hard instances hold between these two extreme cases. So we can check this by this kind of experiment. I guess many of you already have seen this kind of plots. If not, it is very interesting to have a look at it. So to exhibit phase transition phenomena, we consider randomly generated instances. So we are going to randomly generate 3 SAT instances using a uniform model. And in this case, all instances have the same number of variables, which is 400 variables. And each point in the plot here corresponds to an instance. On the x-axis, we report the value of p over n, so this ratio. And on the y-axis, we report the solving time on using some solver. So the higher, the more difficult the instance. And finally, the color of the point tells us if the instance is feasible, if we have found a solution, or if it is infeasible. So we observe that we have on the left of the plot very easy instances, which are all feasible. And then when we increase this ratio, instances are becoming more difficult with a very large standard deviation. And then we arrive in this region where we have both feasible instances and infeasible instances. And the most difficult instances are in this region, which is called the phase transition region. Is it equivalent to the théorie des bifurcations, singularity theory? I don't know. I don't know what is singularity theory. I'm sorry. I will have a look and answer later after the talk. And finally, on the right side, we have only infeasible instances, and the more we increase the ratio, and the easier the instances are, because it becomes easier and easier to prove inconsistency in this case. So more generally, what is a phase transition? This is an abrupt state change from satisfiable instances to unsatisfiable instances. And this change is observed when we change the value of some parameters, which depends on the problem we want to solve. For SAT, these parameters are the ratio between the number of clauses and the number of variables, and the state change occurs when this ratio is equal to 4.26. And this state change corresponds to a hardness peak, which is observed for all solving approaches. Whatever approach you consider, this is also for meta-heuristic approaches, you will observe the same hardness peak on the same instances. So an interesting question is how to predict where is the transition phase, as this region contains the most difficult instances. And to answer this question, you simply have to compute the expected number of solutions. And when the expected number of solutions is much smaller than 1, then you have over-constrained instances and you are in the easy infeasible region. When the expected number of solution is close to 1, you are within the transition phase, so you have the most difficult instances. And finally, when the expected number of solution is much larger than 1, it means that you have a lot of solutions, so it's very easy to find a solution. I'm going to illustrate this on another problem, which is the subgraph isomorphism problem. So the goal is we have two graphs, a pattern graph on the left and a target graph on the right. And we want to decide if there exists a copy of the pattern in the target. So for example, here we have a solution. We have more than one solution, but here is a solution. And this solution is found by mapping every node in the pattern to a different node in the target, so that the edges in the pattern correspond to edges in the target. So here we have found a solution. So now the question is, how can we control hardness of randomly generated instances for this problem? And here is a study. The first question is how to randomly generate an instance of this problem. And to this aim, we have to randomly generate graphs. So first, we consider a model used to generate graph. And for example, we can consider the Erdos-Shreni model, which is a very simple model, where we simply define the number of vertices, n, and we have a second parameter called d, which defines the probability of adding an edge between two vertices. So when d is equal to 0, we have a graph with no edge at all. Whereas when d is equal to 1, we have a complete graph with all possible edges. Okay? So now to randomly generate an SIP instance, I just have 4 parameters. The first 2 parameters define the parameters used to generate the pattern graph, and the last 2 parameters are the parameters used to generate the target graph. And now, how can we control hardness? To answer this question, we are going to vary the values of the probabilities, dp and dt, which control the graph densities. Because our intuition is that when we have very few edges in the pattern graph and a lot of edges in the target graph, then it should be easy to find a solution. And on the other side, if you have a lot of edges in the pattern, but only a very few edges in the target, then it should be easy to show that it is not possible to find a solution. And the hard instances should hold between these two extreme cases. So to check this, we can do an experiment where we fix the number of pattern vertices to 20, the number of target vertices to 150, and the probability of adding an edge in the target graph to 0.4. And finally, we are going to vary the probability to add an edge in the pattern graph. So when this probability is equal to 0, the pattern graph has no edges at all. And in this case, it is trivially a subgraph of the target graph. So in this case, all instances randomly generated will have a solution. So here, I plot one point for every instance randomly generated, and on the x-axis we give the probability dp of adding an edge in the pattern graph, and on the y-axis we have the solving time for a solver, which is Glasgow. And finally, the color of the point tells us if the instance is satisfiable, which is green, or unsatisfiable, which is blue. And now we can see that we have three regions. The region of all satisfiable instances, where all instances are usually quite easy with a very few exceptions. And here you can see the black line here is the average time, average solving time. And we can see that for a given probability, here, for example, when the probability is 0.4, I have a lot of very easy instances, and then a very few difficult instances. Here I have only one instance. That's strange, yeah, and the average is here. But here, for example, on this column, for example, I have a very difficult instance, and that's why the mean here is higher than the majority of instances are here. And we observe this for all NP-complete problems. We always have this kind of results on the satisfiable region. Then on the other side, we have the unsatisfiable region, where instances are more difficult than on the left-hand side, but they become easier and easier. This is because it is more difficult to prove unsatisfiability than to find a solution. And then the hardest instances are in the phase transition region, where some instances are feasible and some others are infeasible. Now we can have a more global picture by varying both the density of for the target graph and the density for the pattern graph. So here on the x-axis, I vary the number of edges in the pattern, and on the y-axis, I vary the number of edges in the target. So for example, on the upper left corner here, all instances are feasible because I have patterns with only very few edges and targets with a lot of edges. Whereas here on the bottom right corner, I have infeasible instances because I have patterns with a lot of edges and targets with very few edges. And the color here it is brown if there is no solution, green if all instances have a solution, and white if half of the instances have a solution and half of the instances don't have a solution. And so I can see that I have an abrupt change between all feasible solution instances to all infeasible instances, and this corresponds to the white points here. And interestingly, we plot here in black our theoretical prediction of where is the phase transition. So we can see that this prediction is quite good, except here there is a small deviation. So how can we compute this theoretical prediction? We simply compute the expected number of solutions given the parameters NP and DP for the pattern graph and the parameters NT and DT for the target graph. So I'm not going to enter into the details of this computation, but it is quite easy to do. So here is the formula which defines the expected number of solutions. And when this formula is equal to 1, this corresponds to the point which is plotted here, to the black line which is plotted here. So we can see that this gives us a theoretical prediction of where are the really hard instances. Now we can check whether it is actually difficult or not to solve these instances. So here is a plot obtained with Glasgow. So with the same X and Y axis. And so for each point in this correspond to 10 instances, and the color of the point gives the difficulty of solving the instance. When it is black, it means that the instance, no instance has been solved by Glasgow within 1000 seconds, whereas when it is white, it corresponds to instances which are solved without backtracking at all. So we can see that the hardest instances are located close to the phase transition. Now we can look at scale-up properties. So here we have instances with only 10 pattern nodes, whereas here we have instances with 30 nodes in the pattern graphs. And here we plot the phase transition, and here we plot the difficulty of solving. So we can see that if we consider instances which are in easy regions, we observe empirical polynomial time complexities. The difficulty slowly increases when increasing the size of the instance. Whereas if we look at instances which are in the phase transition region, we observe exponential time complexities. So it means that the hard instances for which we have exponential time complexities in practice are within the phase transition region. Okay, so now we can compare performance of different solvers to check that we have the same behavior for all solvers. And we notice that for all solvers, when we are close to the phase transition, it's always difficult to solve the instances. And then when we are far from the phase transition, well, depending on the solver, some solvers are more efficient than others. For example, RI is very efficient on very easy instances which are all satisfiable. Less efficient on instances which are over constrained. But all solvers have the same difficulties on the phase transition region. Okay, no questions on phase transition? Now a few words about hardness on for optimization problems. It is different depending on whether you consider a complete approach or a heuristic approach. If you consider a complete approach, then usually you solve an optimization problem by solving a sequence of decision problems. You first solve the problem to find the first solution, and then you add a constraint to find a better solution than this first solution, and you repeat this until finding a solution which is the optimal solution. And the last time is to prove the optimality of the previous solution. So in this case, what we empirically observe is that the first solution are very quickly found, and only the last two instances are really difficult. The penultimate one is the most constrained satisfiable instance, whereas the last one instance is the one where we prove optimality of the penultimate solution. And these two instances are usually the hardest of the sequence. This is the case for complete approaches. Now, if we solve an optimization problem with an incomplete approach, which uses a heuristic to explore the search space, then the difficulty of instances is usually explained by studying the fitness landscape, which is associated with the instance and the algorithm. And to this aim, we build what we call a neighborhood graph. So this graph has a vertex for each possible solution of our optimization problem. And then we have an edge between two solutions if we can build VJ from VA using the mechanisms of our specific meta-heuristic. For example, if we have a local search approach, then these mechanisms are the moves which allow us to move from a solution to another one. So this is the definition of the neighborhood graph. And given the neighborhood graph, we can draw what we call the fitness landscape. So in the fitness landscape, we draw a point for each vertex of V, and the height of this point corresponds to the value of the objective function. So for example, if I have a maximization problem, then my goal is to find the point which is here on the top of this hill. And then I use the neighborhood function to position points with respect to other dimensions. Of course, if I have only 2 dimensions, I can easily draw this figure. If I have more than 2 dimensions, it's no longer possible. But we can imagine what it would be in n dimensions. And so this fitness landscape is used to compute some topological features. For example, a local optimum is a point for which no neighbor is strictly better. For example, here on top of this hill, I have a locally optimal point, and also here. And finally here, I have a locally optimal point, which is also the global optimal point. And the distribution of this local optimal point in this fitness landscape tells us whether it will be difficult or not to solve the instance. Also, we can study the number of plateaus in our fitness landscape. A plateau is, for example, here, a set of points which are all connected and which all have the same fitness value. The same objective function value. And finally, we can also compute the size of basin of attraction, and in particular, the size of the basin of attraction of the globally optimal solution is very important, because any point that belongs to this basin of attraction can be used to find the globally optimal solution by using a hill climbing algorithm. So if I have only one basin of attraction in my fitness landscape, then any hill climbing algorithm using a simple greedy heuristic will solve the problem to optimality. So when we have meta-heuristic approaches, and when we want to study the hardness of instances for these meta-heuristic approaches, we compute this kind of topological features. Okay, no question on benchmark instances. Now, a very few words on, sorry, I'm going to have a look at time. Oops. it's, oops, I can't see what time is it. Okay. Up. So next part of the talk, I am going to very briefly discuss this now, and we will have more example when analyzing the results. So a very important point is to choose our performance criteria. And of course, this performance criteria depends on the question we address in the experiment. We usually have three very classical criteria, which are the duration, the memory consumption, and the quality. And of course, these criteria are interdependent. It is well known that we can reduce the duration of an algorithm by using more data structures. For example, more data structure to maintain values instead of recomputing them from scratch at each iteration. And also, of course, the quality of the solution found by an anytime solver depends on the CPU time it can spend to find the solution. So a few words about the performance measures that can be used to measure the duration. When in some cases, we can simply count what we call dominant operations. These are the cases where we know that the major part of the running time is spent by performing one operation. And a classical example is for sorting algorithms. Sorting algorithm mainly compare elements. So if we want to empirically compare performance of sorting algorithms, we can simply measure the number of comparisons, binary comparisons, which are performed by each algorithm. Another example, when solving constraint satisfaction problem, we can simply count the number of constraint checks. And this gives generally a good idea of the duration of the algorithm. Another performance measure, which is used by Knut in its book called The Art of Computer Programming, is the number of memory accesses, either load a value from the memory or store a value in the memory. The interest of these measures is that they do not depend neither on the language nor on the operating system, the processor, the load of the processor, and so on. So this is very easy to reproduce these measures. However, these measures are not always representative of duration, and in some cases we are obliged to measure the time. So of course, the real time highly depends on the load of the CPU. So we usually don't measure real time, but we measure the CPU time. However, you should be aware that this CPU time actually also depends on the load of the CPU, and it depends a lot on the load of the CPU. That was not true 20 years ago. This is because of new computer architectures. So this is illustrated by Catherine McGeoch on a very simple experiment here. She considers two different computers, HP with 8 cores and Mac with 2 cores. And she ran the same program on one core of these two computers. So on the HP, we have this CPU time, which is quite close to the real time, and this is not surprising. And on the Mac, well, it spans 3 times the CPU times is 3 times larger, but it is also rather close to the real time. Okay, now what if we launch several concurrent processes Here we launch 9 concurrent processes, and all processes solve exactly the same problem with the same input data. So they should spend exactly the same time if we are on the same machine. However, when we launch 9 concurrent processes on 8 cores, we overload the CPU, and so we observe that the CPU time, well, it is slightly different from one process to another when I consider my 9 concurrent processes, but it is much more important than when I launch only one process on one core. It is, well, it is 1/3 larger here. And this is even more important on the Mac because it only has 2 cores. So if I launch 9 concurrent processes on 2 cores, I will increase the CPU time by 50%, which is very important. So when you compare algorithms and when you compare CPU times, you must always have a constant load on your computers, because measuring the CPU time depends on the load of the machine. Of course, the real time also strongly vary depending on the load of the machine, but the CPU time also. Okay, well, I hope everybody actually didn't know that. When I consider optimization problems, I also have different performance measure, and the difficulty for optimization problem is that I usually have two different kind of measures. I have to compare quality of the solution, and I have also to compare the CPU time needed to find a solution. And depending on whether the algorithm is able to prove optimality or not, I compare different things. If the algorithm can prove optimality, then I can simply compare CPU time. But the big difficulty is what should I measure when an instance has not been solved to optimality within the time limit. And then when I have an anytime algorithm, the quality of the solution is continuously improved when increasing the time limit. So I can have different performance measures given the time limit, but the big question is how to choose the time limit. And also when I want to, well, I'm not going to explain this now because I'm going to explain this on examples later. So now let's turn to analysis of the results, and we are going to illustrate this on 3 examples to have concrete things to discuss. But before, just very short introduction to data analysis. So the goal is to transform raw data, that is simply measures, into information. And I have 3 different classes of tools for doing this. I have descriptive statistics, which compute simple values that summarize the main properties of the data. We will see that this is usually not enough, and we will mainly use graphical data analysis, which allows us to visualize the properties. And finally, we can also use statistical tests, which are procedures that allow us to reject or not some hypotheses. A big warning here: before doing data analysis, the first thing to do is to look at raw data. It is always interesting to have a look at the raw data before computing mean values or before drawing pictures. So now we are going to illustrate data analysis for 3 different cases. The first case is to discuss how to compare algorithms which are not deterministic. And we are going to do this on a decision problem. Then we are going to discuss how to compare anytime algorithm that solve optimization problem. In this case, we will have a non-deterministic algorithm too. And finally, we will discuss how to compare algorithms when we have a very large benchmark which contain very heterogeneous instances. There are many other things that we should have discussed today, but we simply don't have time to discuss everything. But just to say that when you have multi-criteria optimization problems, then we use very different performance measures. And also when we analyze data for parallel algorithms, we also have to consider different measures. So first, let us consider the case of non-deterministic algorithms, which are algorithms that use a random function. And in this case, if I run several times the same program on the same instance, of course, I change the seed of the random generator. In this case, I won't measure the same thing because the random function will change things in the execution. So how can I measure performance of non-deterministic algorithms? In this case, I have to consider that each measure is a random variable, and each run is an observation, is a realization of this random variable. So I can empirically estimate the probability distribution of this random variable by performing a large number of runs with different random seeds. So we are going to illustrate this on the car sequencing problem, and our question, which is a very simple question, we will address more sophisticated questions in the next two studies. So I start with a very simple question, which is what is the best parameter setting among 5 given settings of a non-deterministic algorithm for solving just one instance, which is instance number 2682. So what is my performance criteria in this case? I'm going to consider the duration needed to solve the instance. And I have mainly 2 different performance measures to evaluate this duration. First, I can measure the CPU time. And second, I can measure the number of iterations of my algorithm. And as an iteration nearly spans always the same CPU time, I am going to measure the number of iterations. The next point is very, very important, and I will always have this when I experimentally evaluate an NP-hard, an algorithm for solving an NP-hard problem. I know that unless P equal NP, I cannot solve all instances of an NP-hard problem in polynomial time. I will always have instances for which the amount of time will not be reasonable. So I have to limit the duration of each run. In my case, I'm going to limit this every run to 150,000 iterations. So the big question is, what do we measure when we reach this time limits? And in this case, we are going to report the maximum number of iterations. But of course, we know that this is not the real measure. This is just the lower bound of the actual measure. And we must be very careful when we analyze results because this changes things. So now let us start with some descriptive statistics. So for each parameter from 1 to 5, I have performed a large number of runs. Actually, I've performed 100 runs. And I can simply compute the mean measure. So it is reported in this column, or the median measure. And if I do that, I observe that there are very different conclusions which can be drawn depending on whether I consider the mean or the median. Here is the ranking of my parameters if I consider the mean, and here is the ranking when I consider the median. And for example, the worst solver, the worst parameter setting when I consider the mean is the best when I consider the median. So this tells me that I don't have a normal distribution, because in a normal distribution, these two measures have very close values, and this is not the case at all on this experiment. So now to have a better picture, I can try to compute, oh, sorry. What I was telling just before is that actually what I measure in case of failure is a lower bound of the actual measure. So for the three first parameters, there is no failure. So I have the real measures, the real mean and the real median. But the last two parameters, some runs have reached the time limit. So for these two parameter settings, the mean is not the actual mean, but a lower bound of the actual mean. Now I can compute some measures to have an idea of the dispersion of my measures. I can compute the standard deviation, which is reported in this column, but I cannot compute the standard deviation as soon as I have runs which have reached the time limit. I can also measure the difference between the third quartile and the first quartile. The first quartile is the largest value among the first quarter of the lowest values. And the third quartile is the largest value for the 75% lowest values. Okay, so I can compute this range when Q3 is known, but if I have too many failures, then I cannot anymore compute Q3 if I have failures before Q3. And this is the case, for example, for the fourth parameter setting. So the conclusion of this is that reporting mean or median values does not give me a clear idea of the performance of my 5 parameter settings, and the dispersion measures, well, they do not really help me to draw conclusion. What can I do is to plot box plots, which allow me to visualize the raw data, the main values of the raw value data. I visualize here the minimum value for parameter 1, the maximum value for parameter 1, and then the box here correspond to from Q1 to Q3 values, and the green line is the median value. And this gives me a much better picture than previously, and I can draw some conclusions. I can also draw the plot with a log scale, which allows me to see what happens for short time limits. And here I can see that parameter 4 has a lot of runs which reach the time limits, and parameter 5 have some runs which reach the time limit. Now, my question is, what is the best parameter setting? And it's a bit difficult to answer this question because my distributions here are overlapping. So what is the best, which one is the best one is not easy to answer. I can use a statistical test to check hypothesis. I'm going to compare, to do pairwise comparison. So I compare every pair of parameter, and the null hypothesis I want to check is the probability that the time with the first parameter being greater than the time with the second parameter, is this probability equal to the probability of the inverse? If the null hypothesis is accepted, then I can conclude that the results are not significantly different, whereas if it is rejected, I can conclude that there is a significant difference for these two distributions. There exist a lot of statistical tests, and it's always a bit difficult to find the good test. Here, an important point is that my distributions are not normal. So I cannot use a parametric test because I don't know what are the parameters of my distribution. So I must use a non-parametric test, and a very simple test for comparing pairs of experiment is the Mann-Whitney U-test. So I'm not going to explain the Mann-Whitney U-test, but we can simply have a look at the p-value, which is used to decide to either accept or reject the null hypothesis. And when the p-value is very, very small, we reject it. Whereas when it is higher than some threshold, we accept it. So if my threshold is 0.05, then I am going to accept the null hypothesis for the two parameters 1 and 4, whereas if it is lower than, for example, if it is 0.01, I'm going to reject it. And now what I see, this statistical test tells me that I should reject all null hypotheses except for 2, when I compare 2 and 4. This means that 2 is not significantly different from a statistical point of view from 4. But when I look at the actual distribution for given by the box plot, this is actually from proba égale slide 43 time with PI supérieur. Yes, that's it. I don't understand your question because that's the null. My null hypothesis is that these two probabilities are equal. So for the case of parameters 2 and 4, for example, this null hypothesis is accepted. Okay, and usually we conclude that there is no significant difference. And maybe this is not the right conclusion. Maybe it would be more interesting, to compare something else. And well, statistical tests are nice tools to have very short conclusions. Either it is rejected or not. So either the difference is significant or not. But it is usually not enough because, for example, here it tells us that 2 is not significantly different from 4, and from a practical point of view, they have very different behaviors. So a better tool, from my point of view, just do a switch between I and J in the right-hand side. I don't understand what you mean. The left and right of the equality are identical. Yes. Are they? Oh, sorry. You're right. So yes, they should be swapped. Sorry. Thank you very much. Okay, so if I want to compare two random variables, a better tool from my point of view is to compare cumulative distribution function. So what is the CDF of a random variable X? It corresponds to the probability that the random variable is smaller than or equal to a given value. So I can plot this function, and I have done it here for our 5 parameters. Here it is done with linear scale, and I can also use a logarithmic scale, which allows me to better understand what happens at the beginning of the runs. So here my random variable corresponds to the number of iterations, and it means that I plot the probability that the instance is solved in at most x iteration. So for example, here, if I look at, for example, this style limit, which correspond here to 3,000 iterations. For example, I know that I can wait for 3,000 iterations to obtain a result, but this is my real time limit for my application. So I'm interested to find the best approach within 3,000 iterations. So I just compare. Here I can see that for a parameter 1, the probability that it has found a solution is smaller than 0.1. For green, it is a bit higher, but not very high. And then for the blue parameter and the orange parameter, this probability is a bit larger than 0.5. Finally, for the yellow parameter, it has the best probability because the probability that it has found a solution within 2,000 iteration is greater than 0.9. So this gives me a much better picture, which allows me to compare my different parameters. Okay, no question on this. So here I explain how to compute the CDF, but I'm going to skip this because otherwise I won't have time. And I skip to the conclusion of this experiment. And now I can conclude that parameter 1 is dominated by parameter 2 because its CDF is always below the CDF of parameter 2. And parameter 2 is also dominated by parameter 3. However, to choose between parameter 3, 4, and 5, I have to choose a compromise between time and solution quality. If I want to maximize the probability to find a solution within a very short time limit, smaller than 1,000 iteration, then the best parameter is parameter 4. Whereas if I have a lot of time, and I am willing to wait more than 10,000 cycles, then the best parameter setting is the blue one. Okay, no question on this experiment? Now we can have something a bit more interesting and complicated. So now I'm going to consider anytime algorithm, that is an algorithm that produces a sequence of solutions of increasing quality. And of course, the longer the time limit, the better the solution. And most algorithms that solve optimization problems are anytime algorithms. I'm going to illustrate this on the maximum click problem. And the question addressed by the experiment here is given 4 parameter settings of a non-deterministic algorithms. I want to find the best setting for three classes of instances. And in each class, I have several instances. So now I have 2 different performance measures. I have a performance measure to evaluate the duration, and I am going to consider the number of iterations of my algorithm. And I have a performance measure for evaluating the quality. And in this case, it is the size of the click, and the larger the size, the better the solution. So the first question is, I have two criteria, but maybe I can fix one of these criteria and only study the other criterion. So maybe I can study each criterion separately. The first case is I fix the quality. I want to find a click of size k, and I plot the cumulative distribution function associated with the duration for the decision problem, which is, am I able to find a click of size k? So here is the kind of plot I obtain. For so here I have 100 execution for each parameters. And on the y-axis, I have the probability of finding a click of size 57. And 57 is the optimal solution for the instance that I am considering, which is instance C500. And here I have a problem because only 2 parameters have been able to find a solution for at least one run among the 100 runs. And actually it's only the blue parameter finds quite often, but less than 20% of cases, the optimal solutions. And here it's very rare. And I have 2 parameters for which I never find the best solution. So it's difficult to compare my different parameters. So maybe I can plot this CDF for different values of K. But now, depending on the value of K, the conclusions are different. For example, here, if I choose a small value for K, it's quite easy to find a click of this size. And in this case, the best parameter is parameter 4. Whereas if I consider the optimal value for K, then the best parameter is parameter 3. So this is not a good idea to fix the quality and plot the CDF associated with the duration. And I will have exactly the same conclusion if I fix the number of iterations. So I fix a time limit and I plot the CDF associated with the quality within this time limit. For example, if I fix the time limit to 3000 iterations, then here is the CDF, which gives me the probability of finding a click of size X for different values of X. And I can compare my different parameters. And in this case, the best parameter is the blue parameter, because it has a probability of 1 to find a click of size up to 54, and then it decreases, but slower than other parameters. However, if I change the value of t, I change the conclusion. If I fix the time limit to 1000 iterations, then the best parameter is the yellow one. And when I shorten this time limit, I notice that I have 3 parameters which have nearly the same performance. And the best one is the yellow one. So if I fix the number of iterations, the big question is how to choose the number of iterations. Well, if I am not fair, I can choose the limit, which is the most favorable for my approach. For example, if I want to favor the yellow approach, then I will choose t equals 1000, but this is not fair. And when I review papers where they fix the time limit, I always ask what if we change this time limit? If it is shorter or larger, does this change the conclusion? So we obtain much better conclusion if we plot the evolution of the quality with respect to the duration. So on the x-axis with a log scale, I plot the number of iterations, and on the y-axis, I obtain the expected size of the best click within this time limit. So this gives me an empirical estimation of the expected size for all the possible number of iterations. Now, my problem is that this is the plot for one graph, and I have different graphs for different classes of graphs. And I would like, of course, I'm going to plot this for every graph just to have a look of the tendency, but then I would like to aggregate plots of different instances. And in this case, the maximum click have different sizes. Here, the maximum click has a size of 57. But if I average this plot with a plot where the best click has a size of 10, I will obtain something which is not significant. So in this case, I have to normalize the measure. There are two classical ways to do this. In both cases, we divide by the value of the objective function for the optimal solution, which which is S star, and I can either plot the gap to the optimal solution. So I compute the gap between the largest possible click, so the optimal click, and the click I have found. And I divide this by the optimal click, and I obtain a gap in percentage. So for example, here, if I have here for the yellow, it is 0.1 at less than 100 iterations. It means that I obtain a click which is 10% lower as the optimal click within 100 iterations. Okay. And quite similarly, I can plot simply a ratio between the current solution and the optimal solution. And in this case, if I have a ratio equals to 1, then I have the best solution. So when I plot the ratio to the optimal solution, the higher the better. Whereas when I plot the gap to the optimal solution, the lower the better. And in this case, the optimal solution is when I reach 0. So now that I have normalized the measure, I can compute average expected quality with respect to the evolution of time. And I do this separately for each class of graph, because I observe that the results are quite different when I change the class of the graphs. For the gen graphs, which are quite easy instances, the best solution is obtained. The best parameter setting is parameter 4, because so here I have plotted the average gap. So it means that it finds the best solution in 100 iterations on average for all gen graphs and all runs for each of these graphs. Whereas on C graphs, the yellow parameter is the best one for short CPU time limits, but when I have longer CPU time limits, the blue parameter becomes better. And probably that if I would have increased the CPU time limit, the green parameter would have become even better than the blue one. And finally, the third class of graph is the Brock class. And on this class, which is very strange, the best parameter setting is the parameter 1, which actually I can confess it now. It is a random. It is random search for the purple parameter. So of course, if I expect to do, I expect that my algorithm do better than random search, and this is the case for the gen and the C graph. And the parameter 4 has very intensively search, whereas parameter 2 is very diversified search. And so the question, and I'm not going to spend a lot of time on it, but I find it very interesting. When you observe very different conclusions on different kinds of graphs, then it is always interesting to try to understand why you observe these different conclusions, and in particular, why random search is the best approach on the Brock graphs. And we can explain this by looking at the fitness landscape of these graphs. So I consider only one graph of the class, and I consider the smallest graph of the class, and I plot here 1 point is for each optimal, locally optimal solution. And for each locally optimal solution, I plot on the x-axis the size of the click, so the quality of the solution, and I plot on the y-axis the number of vertices which are shared with the optimal solution. So for the case of the gen, I see that I have a perfect correlation, a very nice correlation And the optimal solution, which is here, shares a lot of common vertices with the second best clique and so on. So once I have found a clique here, my search will be, if it is intensified, it will easily find this point. Whereas here I have the inverse phenomena. The optimal solution is here. And the second best, so it has 17 vertices. And then I have 4 cliques with 16 vertices. And these cliques only share only very few vertices with the optimal solution. In other words, the optimal solution has been hidden around very bad solutions. So in this case, the best approach is random search. Okay, so would it not be better to compute the best average gap with a subset that contains all classes of graphs? Well, of course, you can then also compute the best average gap for all classes of graphs, but you will merge curves with very different shapes, and you will obtain average conclusions. But and that's my conclusion for this experiment. When performance change from an instance to another, I think it's more interesting to analyze performance for each class of instance separately, and we will see that in the next study. If we take all instances together, we have some conclusions which may be misleading. So it's interesting to group similar instances and to analyze performance for group of similar instances separately. And then what we will see in the last part of the talk is that we can always use automatic selection and configuration techniques to find the best parameter setting and the best approach for each group separately and for each instance separately. So the last, and I need to have a look at the time I still have, sorry. Okay, I still have half an hour, so I think it should be okay, but I need to go quite fast. So the last study, I am going to consider a problem, which is the subgraph isomorphism problem, for which I have a very large benchmark of thousands of instances. And my question is, what is the best solver among 4 well-known solvers? Here, my performance measure is, so this is a decision problem, so not an optimization problem. So either I have solved the instance or I haven't solved it. So my performance measure is the duration, and to measure the duration, I must consider the CPU time because I have very different solvers. So I cannot count the number of search nodes or the number of iterations. I must limit each run, the time. I must add the time limit for each run because this is an NP-complete problem. And for example, we have made experiment with a limit equals to 100,000 seconds. And even with this time limit, some instances are still not solved. So I must put a limit, and I choose a limit which is reasonable because I have a lot of instances. So I consider all instances coming from 8 existing benchmarks. So I have more than 14,000 instances. And these are very different benchmarks. Some are coming from real applications. I also have a lot of random instances. And I also have a benchmark which is coming from a graph database which has been done by Knut. And this database contains very different classes of graphs. Here I plot each point corresponds to an instance, and on the x-axis there is the number of nodes, and on the y in the pattern graph, and on the y-axis I have the number of nodes in the target graphs. And here this is the same for the edges, and it shows us that we have very small instances with graphs which have 10 nodes, both in the pattern and the target, and we also have rather large instances with a graph which have more than 1,000 nodes and a lot of edges too. So the first question, I'm going to go very fast on this, but it is, where do you find the most relevant benchmarks for your experiments? That's a very interesting question, and I cannot answer it very quickly because of course you have to study the literature and use the benchmark, the public benchmarks that everybody uses. But sometimes the public benchmarks are not that interesting, and sometimes you also need to add a new benchmark, real world benchmarks, and also randomly generated benchmarks and so on. And for example, for this study, initially the only known benchmarks was the random instances, except this one, which is a very difficult benchmark that we have added recently. And also the well-known benchmark is this one. And we have added instances coming from real applications to try to broaden the study. But we will see that the conclusions strongly depend and are different from a benchmark to another. So choosing the benchmark allow you to choose your conclusions, but this is not a good practice, and you should consider as many benchmarks as possible. So here, a quick slide to say that we cannot plot the evolution of time with respect to the size of the graphs. Here, I show examples. So here the results, for example, with Glasgow. On the x-axis, I have the time limit, and on the on the y-axis, I have the time limit, and on the x-axis, I have the number of nodes in the pattern graph. And I can see that for very small values, for example, here it is 20 nodes, some instances are very quickly solved, and some instances are not solved within the time limit. So I cannot compute an average for these values, and even if all instances were solved, I see that the standard deviation is very high. So computing average values on this kind of data is not interesting. And this is for Glasgow, but if we look at RI, this is even more, the standard deviations is even larger. Okay, so now I can try to compute a few short statistics to try to answer my question. So for example, I can compute the number of times a solver is the fastest among the four solvers. So among the 14,000 instances, I count the number of times a solver is the fastest. And the winner in this case is RI. And this is amazing because for a wide majority of instances, it is the fastest to solve the instance. Now I can also look how many instances are solved within the time limit. And in this case, the winner is Glasgow. And RI is the third best one, so it's far from being the best. But if I change the time limit and I take a very short time limit, now the winner is RI, and Glasgow is the worst one. I can also try to compute the average time, but as some instances are not solved, I can compute the average time over the solved instances, so within the time limit of 1000 seconds. So here is the average time of Glasgow on the 14,356 instances. But for LAD, for example, I report the average time on these instances, and these are not the same sets of instances, so it is difficult to compare these average times, but this gives me an idea anyway. And finally, I can also compute a bound on the average solving time. In this case, I consider all instances, and when an instance is not solved within the CPU time limit, I just consider that it spans 1000 seconds. But in this case, the value I obtain is the lower bound of the actual value. So the first conclusions are or that there is no clear winner. Sometimes Glasgow is better than RI, sometimes RI is better than Glasgow. And well, LAD is always the second best solver for the 5 considered statistics. So maybe LAD is a good solver, I don't know. So I need to visualize the data. The classical way to do this is to plot what we call the cactus plot, which is the evolution of the number of solved instances with respect to time. Here is how to compute, how to produce a cactus plot. I'm not going to explain the algorithm, and just have a look at the result. On the left, it is with a linear scale, and on the right, it is with a logarithmic scale. And so on the x-axis, I have the number of solved instances, and on the y-axis, I have the CPU time. And for example, here I can so I'm going to draw it up. If I want to compare, for example, my CPU time limit is 10 seconds. If my CPU time limit is 10 seconds, then I draw this line. Imagine that it is straight. And I look, it means that the number of instances solved by VF2 within a time limit of 10 seconds is this. And so this is the worst solver for this CPU time limit. The second worst is RI, and then the best is Glasgow, and the second best is LAD. Okay, for the cactus plot, I guess most of you are familiar with this kind of plot. So a slightly different kind of plot is the cumulative distribution function, which I already introduced for previous case studies. And now I'm going to plot the probability of success with respect to time for my benchmark. So I easily obtain a CDF from a cactus plot simply by dividing the number of solved instances by the total number of instances. And also I invert the two axes. So now I have the time here and the probability of success on the y-axis. Another interesting thing to do is to plot the CDF for the virtual best solver. The virtual best solver is a solver that does not exist. And we imagine that this is the solver which obtains the best performance for each instance separately. So for each solver and each instance, I note TIS, the time of solver S on instance E, and the time of VBS for instance E is equal to the minimum time over all the solvers. Okay, for what is a CBS, VBS? So here I plot in yellow the CDF of the virtual best solver. And this shows me that, for example, if if RI, the plot for RI was merged with the plot of the VBS at the beginning of the solving process, it would mean that the best solver for short time limit is always RI. But as there is a gap between the VBS and RI, it means that for some instances, one of these solvers are more efficient than RI, even for short time limits. Okay. Now, in some cases, we can also plot performance profiles, and performance profiles are quite easily obtained by from the CDF of the VBS. Actually, the performance ratio of a solver S on an instance I, which is denoted RSI, it is equal to the solving time of S on instance I divided by the solving time of the VBS, so the virtual best solver. In other words, the best solving time among all compared approaches. So if R is equal to 1, it means that S is the best solver for this instance. And if R is greater than 1, it means that the solver S is R times as long as the virtual best solver. And now I can plot the cumulative distribution function of this performance ratio. And I obtain the probability that the solver S is within a factor X of the virtual S solver. So for my curve here, if I looked simply at, on 1, when x equals 1, it gives me the percentage of instances for which a solver is the best. So for example, Ri is the best solver for more than 80% of the instances. Whereas Glasgow is the best solver. So Glasgow is in purple, and Glasgow is the best solver for 10% of the instances. But now if I consider the ratio for 1000, sorry. Okay, so now I look, and here I see that Ri is the time spent by Ri is smaller than or equal to 1000 times the time of the VBS. So it is within a factor of 1000 from the VBS for 93% of the instances, whereas for Glasgow, it is for 97% of the instances. Okay, so now I have a big picture, but I have a warning here, which is that my benchmark here is a very heterogeneous benchmark, which contains very easy instances and very hard instances. And actually, I have a lot of very easy instances and only a few hard instances. So maybe I will obtain a different conclusion if I study for each benchmark separately. So for example, there is a benchmark which comes, this is a real application, and it contains a lot of instances. And all these instances are very easy because all solvers are able to solve all these instances. And on these easy instances, Ri is amazingly fast. He is incredible because he is able to solve all instances within 0.1 seconds. Whereas all other solvers need much more time on these instances, which are very big instances. And actually, Glasgow and LAD have not finished to pre-compute some pre-processing steps. They have not started to solve the instance, whereas Ri has already solved the instances. So we can see that on these instances, Ri is the VBS because the two plots of the VBS and of Ri are exactly the same. So on this benchmark, the best approach is Ri, and there is no competitor. And we can see on the performance profile, because the performance profile for Ri is simply this is the vertical line, meaning that it is always the best for all instances. Now I obtain different conclusions on other classes. Here is a second class of real-world instances, and on this class where Ri is good at short CPU time limits, but then LAD becomes better, and finally Glasgow is the best one at the end. And I can see that on this benchmark, the VBS is higher than all other benchmarks. So there is no single winner on this benchmark. Then for LV, this is quite the same conclusion, no single winner. And for the random instances also, I don't have a single winner. And here I don't have a single winner, though Glasgow is really much better than all other approaches. But for short CPU time limits, sometimes Ri is better. And so the VBS is sometimes a little bit higher than Glasgow. And finally, here are the very, very difficult instances which have been randomly generated by using our work on phase transition. So we have deliberately built very difficult instances, which are very small instances with only 30 nodes. And on these instances, the VBS plot and the Glasgow plot are the same. So on these instances, Glasgow is the best solver and the single winner. Okay, now another thing that I can do to compare two solvers, because my conclusions are that I have, well, RI is very good for short CPU time limits and on some easy instances, whereas Glasgow is very good for longer time limits and hard instances. So if I want to compare just these two solvers, a good image is to plot a scatter plot. So on the x-axis, I plot the time. So each point corresponds to an instance. And the value x gives the CPU time for Glasgow, and the value y gives the CPU time for RI. So every point which is below the gray line, and the gray line correspond to x equals y, every point which is below is solved faster by RI than Glasgow. So here is where RI is winning, and here is where Glasgow is winning. And the color of the point gives me the class of the benchmark. And here I can see my image benchmark in purple, and I can see that RI is very fast on this benchmark. But on the opposite, I can see here a lot of instances that are not solved by RI, whereas they are solved by Glasgow in less than 1,000 seconds. And for example, the very difficult instances are these triangles here. And I can see that there is a lot of triangles here, which correspond to instances which are not solved within 1,000 seconds by RI, but they are solved by Glasgow. So this allows me to compare on a per instance basis two solvers. And my conclusion is that, well, both solvers have interesting features. So I would like to combine these two solvers actually, and that will be what we are going to see after this. I just have a look at the time. Okay, so I have just 15 minutes for well, the conclusion is that well, don't forget to experiment your solver on very large, on very difficult instances, which usually are not so large. Okay, we have seen a lot of different kinds of plots, and here is an advertisement for a tool that you can use. This is a web application, and you give your results to, so this is a file, a CVS file to this application, and it will plot a lot of figures to compare different solvers. So have a look at it. So my conclusion is that the conclusions are very different from a benchmark to another. So of course you must consider as many benchmarks as possible, and not only those that are favorable to your solver, of course. And it is better to analyze results for each benchmark separately, especially in case of unbalanced benchmarks. If I have a benchmark which contains a lot of instances, and then another benchmark which contains only a very few instances, if I plot a general picture for all benchmark, then the large benchmark will the conclusion will be the same than those of the large benchmark. So it is always interesting to plot for each benchmark separately. And finally, we should use automatic selection tools to improve performance. And this is what I'm going to quickly show you in the last part of this presentation.
So first, have a look at automatic configuration. So usually a program has a lot of parameters and hyperparameters. Parameters are the variables that define the thresholds, weights, frequencies, and they change the performance of the algorithm. For example, the length of the taboo list for a taboo search is a parameter. We usually also have hyperparameters, which are variables that change the algorithm because they correspond to design choices. For example, when I do local search, I can consider different neighborhood functions, and this can be I can have a parameter of my program which which allow me to choose the neighborhood function. The same is for when I do constraint programming. I can change the filtering algorithm, and this change the algorithm. Okay, in what follows, I'm going to call parameters, both parameters and hyperparameters, because now I'm going to be interested in how to tune these parameters. But first of all, let me introduce the vocabulary which is used for experimentation, not only in computer science. And for experimentation, we call a factor, a parameter, which is studied in the experiment. So in the experiment, we are going to change the value of this parameter. So the factors are the important parameters, and all other parameters, we simply fix their values. Now for each factor, we have to identify the levels, which are the set of possible values for this factor. So for symbolic factors, I always have one level per value, but for numeric factor, if this is not discrete values, then I have to identify intervals of relevant values by sampling. Now, what I call a configuration is an assignment of one level to each factor. This corresponds to one configuration of a solver. And we call a design point a configuration that must be experimentally evaluated. Ideally, we would like to evaluate all factor level combinations. And this is called full factorial design. When we do full factorial design, we evaluate all possible combinations of levels to factors. This is called grid search or hypergrid search when using machine learning tools. And the problem of this full factorial design is that we usually have an exponential number of combinations with respect to the number of factors. So usually we cannot do full factorial design. And this is a pity because this allows us to identify all factor effects, including interactions between factors. So usually we cannot do full factorial design, and we do fractional factorial design. And now we have to select a subset of configurations that will be evaluated in order to choose the best one. So in many cases, we do this manually, and this is called manual parameter tuning. But if we do this manually, we have several drawbacks. First, it is very time consuming. Second, we usually have intuitions. We think that the temperature of our simulating annealing approach should be between this value and this value, but these intuitions may be misleading. And the third drawback is the most important one from my point of view. We usually spend a lot of time to tune our approach. But then we compare our approach with approach of other people. And when we tune these other solvers, we do not spend the same time. And so this is not fair. And finally, when you do manual parameter tuning, this is not reproducible. You cannot, in a paper, say, well, this is how we have done, and if you do like this, you will obtain the same conclusion as we have if this has been done manually. So Holger Huss has introduced what he called programming by optimization, and I really like the idea. The idea is that when you develop a program, you introduce a lot of parameters, and then you can automatically configure your hyperparameter, your program with a lot of parameters and hyperparameters by using automatic configuration tools. So just a few words about automatic configuration. So the problem of automatic configuration is given a set of configurations for an algorithm and a distribution over a set of instances and a performance measure. Our goal is to find the configuration which optimizes the expectation of the measure for the instances which correspond to this distribution. So how to define the distribution? I'm going to skip this because maybe I still have time. I really, oops, sorry. No, I don't have time. So I'm going to skip this just to give an example of automatic configuration tool, which is SMAC. And so you can use it, have a look at the source code here, and the paper is here, and two other examples for which you can use them because the source code is available, or it is available as a R package, is param-ELS and iterated phrase. And all these automatic configuration tools allow you to automatically tune your solver, and this allow you to find the best. When you use these tools, you are fair with all solvers, and in your paper you can simply say, I have used this tool with these parameters, because these tools, of course, they also have parameters, so you have to specify the parameters, and then your experiment is reproducible. We can redo the tuning exactly the same way as it has been done. Another complementary approach is algorithm selection. So automatic configuration is really nice to find the single best solver, so SBS. But we have seen that SBS may be very far from the virtual best solver when instances are heterogeneous. So that was our conclusion on subgraph isomorphism problem. On some classes of instances, the single best is equal to the virtual best. This is the case here. And in this case, we don't have to do automatic selection. But for other benchmarks, there is a gap between the single best and the virtual best. And in some cases, for example, here, I don't even have a single best. For example, here, the single best for short CPU time limits is RI, whereas for large CPU time limits, it is a LAD and then a Glasgow. So in this case, I should use automatic selection. So this is called a per instance algorithm selection. And the goal is given a portfolio of algorithm and an instance to select the algorithm which is expected to perform best on this instance. And to solve this problem, this is usually done in two steps. The first step is called offline, because we do it before solving instances, and this is a training step because we use machine learning. So this offline training, we consider a distribution of instances. We have a performance measure. We also embed each instance in a feature space. So we describe each instance by a vector of numerical values. And then the goal is to build a model, which is called a selector, that given a vector of features, select the algorithm of the portfolio, which optimizes the measure when I use this selector, the algorithm selected on my instance. So this is done offline. So I learn a selector, and then when I have to use it to solve a new instance, I simply return the algorithm selected by the selector, given the features extracted from this instance. So 2 examples of existing automatic selection approaches, which are available, so you can have a look at these papers, and you will have you can download these approaches. There are related problems, but I'm going to skip this. I wanted to illustrate very quickly on subgraph isomorphism. So here I have the CDF of the virtual best solver in orange compared to 8 different solvers, and we can see that we have a huge gap between the single best and the VBS for short time limits. So we have use this approach. So offline, we have trained a model. Online, we have done something a bit different, because we first run 2 very fast and complementary algorithms before trying to select a solver. This allows us to solve very easy instances without using selection. And this allows us also to collect dynamic features for the instances that are not solved by the algorithms. And then, if the instance is not solved, we extract the features from the instance, and we ask the model to select an algorithm given the features. So here are the features. I'm not going to enter into the details, because I think, yes, I still have 1 minute to show you, to tell a few words about Llama. Llama is a package which is integrated in R, so you can use it. And it is a really nice tool for per instance selection, but also for analyzing performance. As input data of Llama, you must give features of instances, and you must also give performance data, so all your performance measures. But then Llama, it does not only do selection, but it also does a lot of experimental evaluation, which are really highlighting and very interesting. So really, I think it's a good idea to have a look at Llama when you have developed several algorithms, and you want to see if you could obtain better results by combining these algorithms simply by selecting the best one for each instance. And that's my final word, is that was the result of subgraph isomorphism, but this is not very important. And the conclusion is that it's very easy to obtain huge amounts of experimental data. And actually, it's much easier than is in other sciences, such as biology, for example. And maybe because it's easy to obtain huge amounts of experimental data, maybe this is because I think we are really bad at collecting and analyzing experimental results in computer science compared to other sciences such as biology. Maybe this is because it is so easy to do these experiments. However, we should always be careful not to kill our machines, not to run experiments that are useless. So experiments should be carefully prepared. And also, it's quite difficult to extract interesting knowledge from experimental data. So we should use appropriate data analysis tools. And it is always a good idea to use automatic configuration to tune parameters. This is much fair, and it is reproducible. And finally, use algorithm selection to exploit algorithm complementarity, and this will allow to obtain a much better approach. And that's my final conclusion. And if you have any questions, so I'm sorry, I'm a bit over the time, but if you have any questions, I'd be happy to answer them. A possibility also that you email me if you have any question. For the platform, Discord platform, I can try to I can try to be there, but somebody should send me the URL for the platform. Christian maybe could send me
Yes,
the.
yes, of course. I will give you the link.
Okay, I see there are some chat remarks, and I have not looked at the chat. You were giving me the. Thank you for the hour. Programming by optimization, same kind of concept for general grammar. Ah, nice, very good remark. I didn't know that. So, okay, if you have any questions, I can stay here for answering questions. Otherwise, you can.
Did you answer the question that is still open in the Q&A? I don't remember. Sorry.
Yes, I think I did.
Okay.
It is better to compute the average time for common solved is it better to compute the average time for common solved instances? Well, actually, I don't think it is. Well, we can do it, but if you only keep the common solved instances, then you will discard all instances which are hard for a solver but solved by another one. So that's not fair, because you will keep only easy instances. So on easy instances, some solvers are very good on easy instances, but bad on hard instances. So I have coded my for solving in Python. However, the data is coded in C++. That's a very good question. The best way to compare in this case is to identify a dominant operation, a number of iteration, a number of constraint check. If you can do this, then you can compare whatever the language is. Well, Knut counts the number of memory load and store, for example. But usually it's very difficult to do that. And also you need to compare your, to modify the state-of-the-art algorithm. So you have to enter your runs in the C++ code too. So when this is not possible, then it is very difficult to compare because, for example, when you compare Java to C, a common practice is to say, well, we have a factor 4. So Java is 4 times as long as C, but that's a very general ratio. And depending on what you're doing, maybe this is not the case. So that's a real problem. Now, if your Python algorithm is much better than the C++ algorithm, then you will win. There is a very interesting paper at CP this year, which has compared different, for SAT, it has taken state of the algorithms solvers of 20 years ago and computers of 20 years ago. And they have asked the question, which is the winner if I take an old algorithm on a new computer, or an old computer and a new algorithm? And the winner is the new algorithm, because if the progress we do with algorithm is much more important than the progress we do with programming languages and things like that. So I'm not sure I've answered your question. So multi-core implications for performance. High performance are good. That's a very, very good question. And I really have it because I use clusters for my experiments, like a lot of people. So in this case, I cannot control the load of the computers. We can simply hope that the load is constant. And I have discussed with the computing center, which is performing the experiments for me, which is IN2P3. This is the computing center for nuclear physical. So they are in Lyon, so I have discussed with them. And actually they do have a rather constant load on their course, because they have scheduling algorithms for planning the experiments, and they try to always have their computer which are fully loaded. So you can hope that the load is constant. Well, repeated runs could be a solution, but this is a pity, because this is expensive for well, running experiments that's using energy and computers, and sometimes experiments are very time consuming. So if you need to do the same experiment 10 times just to obtain an expectation of a time, this is a pity. But that's a very good question, and I don't have the answer.
Okay, thank you, Christine. It's a pity also that we cannot applause because I think that your talk was really appreciated. So I do it myself, but it's not enough. Anyway, I think that your lectures should be given at the beginning of each PhD thesis in our field, either operations research or constraint programming or any computer science domain. Finally, so maybe your video could be advised. For every doctoral school. So I sent you the Discord platform on the chat and also by email, because I have to close the session. So if you have a bit time this afternoon or before Denis' talk, for example, the talk of this afternoon starts at 2:30 p.m. So if you have time before, for example, to discuss, maybe we'll have more questions on Discord.
So I need a little time to have a pause, and I have a meeting at 3 p.m. So maybe I can try to answer questions from 2:30 to 3, if it's okay for you.
Great. Okay.
I will try, but I am always available by email, and so you can send me emails, and I will be happy to answer you, even if it is to say that I don't know the answer.
That's great. Thank you again. Thank you for the numerous participants today. And so see you at 2:30 here on Zoom to attend the lecture of Denis Tristram on machine learning applied to scheduling in distributed systems. Thank you.
Okay, thank you.